Lesson 2.1, derivatives of polynomial functions. So we've been introduced to derivatives as they relate to the slope of a tangent line or the instantaneous rate of change of a function or of a curve. We also know that the derivative of a function is another function. So now we're going to start actually differentiating and finding the derivative of different functions. And before we do, we're going to just copy down a handful of the derivative rules. You already have some of these as they apply to limits, I think, but as derivatives, they work the same way. And we've got the constant rule, which states that if f of x is a constant, if the function that you're dealing with is a constant, which is just a straight horizontal line, then the derivative of that is 0. That makes sense. If you have a horizontal line with a slope of 0, then the tangent at any point, the slope is going to be 0. So the derivative is 0. Okay, good. Power rule. The power rule says that if the function f of x is x to the power of n, and remember, this is why we're going to be breaking our polynomials into terms and dealing with them term by term, because each term interacts differently. You might have a term that has a power of x to the power of 2, but in the same polynomial, you might have to apply the constant rule to the term that is a constant. The derivative of this, really important. Here's what happens. N gets put down in front as a multiplier. The exponent comes down, and the exponent gets dropped by 1, n minus 1. So it looks kind of confusing in this notation, but as we work through it, it actually becomes pretty straightforward. Then we have the constant multiple rule, not to be confused with the constant rule. I'll probably just call this the multiple rule or the scalar factor rule or something like that. But it basically says that if f of x is a function that has a constant multiplier in front of another function, so something like, well, there, x squared would be a function and the constant multiplier is 2. Okay, so that's just an example of what this could look like. The derivative of this is c times, so that constant just stays out in front, times the derivative of that function. Okay, so how does that work out? Well, if we use our power rule here, and our constant multiple rule, the constant multiple rule would say, I'm just going to do this, let's say we had f of x equals 2x squared, then this should say f of x, then f prime of x, I keep that constant there, and then I differentiate the x squared, which is 2x, which will get you a derivative of 4x. Okay. Next is the sum rule. The sum rule says that if you have two differentiable functions and you add them together, so you have h of x equals f of x plus g of x. Okay, f of x and g of x here are both differentiable, and we're adding them together. Then it's also true that the derivative of h of x is the derivative of f of x plus the derivative of g of x. H prime of x is equal to f prime of x plus g prime of x. And the difference rule works the same way. The difference rule states that if you have a function, h of x, and it's made up of, it's the difference between two other functions, and both of these functions, f and g, are both differentiable, then h prime of x is equal to f prime of x minus g prime of x. And I'm not going to do this for all of them, but we also have, so this is called Lagrange notation, f prime of x, g prime of x, that's Lagrange. But we also did Leibniz. And basically what that is the derivative of f of x equals c is written this way. D over dx, or d by dx, of, with respect to c, equals 0. So here we have the constant. So basically all this is saying is maybe I should do, like, this would be, the first one here would be like f of x equals c is the original function, and the derivative of that function with respect to the constant is 0. Okay? Same thing here. And you might even get it in y. So let's say our original equation was y equals x to the power of n. Then you would say d over dx or dy over dx. You'll see it both ways. D over dx of x to the power of n is nx to the power of n minus 1. Okay, this is saying the derivative of this function, the derivative of f of x, is this with regard to the power rule. Okay, good enough. You could do that all the way down. Example 1 tells us to show that the derivative of f of x equals radical x is f prime of x equals 1 over 2 times radical x. Okay, so again, that looks pretty ugly. Two things we notice right off the bat is we have a square root. We don't have any laws to deal with square roots, so we're going to need to convert that into an exponent. And then this looks pretty ugly, but we'll see how that gets created as we go through it. So if we start with f of x, which we're told is radical x, and we go from square root form into exponent form, we end up with x to the power of 1/2. So now all we need to do is differentiate that, which means we're finding f prime of x, and we are applying the power rule because we have an exponent. So by the power rule says that we can take that exponent, move it out front, and the power is going to go down by 1. So I'll write that we had a power of 1/2, and we're going to subtract 1 from that exponent. Again, once you get good at this, you can do it in fewer steps. But in my exponent, I'm subtracting fractions, so I want to express 1 as a fraction over 2, which is simply 2 over 2, which leaves us with an exponent of negative 1/2. A negative exponent would bump us into the denominator to have a positive exponent, and exponent of 1/2 is the same as the square root of x. Okay, so 2 steps here. This piece gets bumped into the denominator to have a positive exponent, and I convert from exponent into square root form. It's kind of insane. And there you have the derivative. This will give you the slope of the tangent at any point along radical x. The graph of radical x. That takes us to example 2. In example 2, we're just applying the power rule. So we have polynomials with one term, and we're going to find the derivative of each. So in the first one, we're given y equals the cube root of x. Okay, so right away, cube root, we don't have any rules derivative rules expressly to deal with that, but what can we do? We can put this into an exponent. So the cube root of x is equal to x to the power of 1/3. And now we have something that we can apply the power law to. So this is still y. Okay, we haven't differentiated yet. But now with the power law, if we're going to differentiate, we're going to find dy by dx. Okay, what are we allowed to do? Well, we take this exponent, and he comes down in front as a multiplier, and then the exponent goes down by 1. Okay, so we'll do it in 2 steps. We've got 1/3 out front, and then our exponent. In the exponent is going to go down by 1. I've already put 3/3 as my fraction over 1 so that I can subtract my fractions here. So we have 1/3 times x to the power of -2/3. And this one asks us to express our answers using positive exponents. So if I have x to the power of a negative exponent, all I have to do is bring that down into the denominator. So my numerator is 1. Denominator is 3 times x to the power of 2/3. And that is differentiated. B, there are 3 of these, by the way, A, B, C. B is y equals 1/x. Again, this is, I need the x to be in the numerator, so it's going to have a negative exponent, so 1/x is the same as x to the power of -1. From there, I can differentiate. dy by dx is equal to, now when my exponent comes out in front as a multiplier, using the power rule, basically it's going to be -1, but I just need to keep the negative sign. That's -1x now. And my denominator is going to go down, my exponent goes down by 1 to -2. The problem asks me to express this with a positive exponent, so that's going to bring my x squared into the denominator. X to the power of -2 is the same as 1/x to the power of 2. With the negative sign, I put mine up top, but it should really go out in front at the end. Done. Okay, so just applying these rules carefully as we move along. The next one is y equals -1/x to the power of 5. Okay, so they put a negative out in front just to make it a little more challenging. What we're going to do first is express x with a negative exponent, bring it into the numerator. So y is going to look like this, -1. Okay, and you can put that in brackets so you know it's still there, even once we differentiate. And then we're going to have x to the power of -5. Okay, again, you could write this with just a negative sign out front, then you really have to remember to multiply your exponent by that negative. It's just as easy to kind of keep it here, then you can see your -1 is still available, it's still there. And we can differentiate this using the power law. Again, the exponent becomes a multiplier out front. So I'm going to do that in one step. -5 times -1 is just +5. And then my denominator goes down by 1. So I'm at -5, it goes to -6. And I need to express with a positive exponent. So this is 5/x to the power of 6. So that is differentiating polynomials that only have one term, monomials. And we applied the power rule. The next example has us doing polynomials with more than one term. Okay, so we'll be applying a few different rules. Example 3. A. We're going to name the derivative rules that we're using. So we're given y equals 5x to the power of 6 minus 4x to the power of 3. There are 4 of these, by the way, if you're thinking about your spacing. And I'm going to basically work down here and write the rules as we go along that we use. All right, this one's pretty straightforward. We are going to use the constant multiple law. So this 5 is going to stay out front, and we're going to differentiate x to the power of 6. Okay, and we're going to use the difference law because we're taking the derivative of this whole thing, which basically means we can just take the derivative of this part and subtract the derivative of that part. You do that without thinking. You do that even if you didn't know that law. You just bring that negative sign down. And over here, same, we have a constant multiplier out front, and then we're going to take the derivative of x cubed. So this is what it looks like. Y prime is equal to, and again, I'm going to do it in a couple of steps, even though eventually you'll be able to do this pretty quickly in your head. So now I'm just going to take the derivative of x to the power of 6, which is 6x to the power of 5. Okay, the exponent became a multiplier out front, and the exponent dropped 1. I have my negative sign, and then I take this 4 stays out in front, and I just take the derivative of x to the power of 3, which is 3x squared. And now I simplify. That is 30x to the power of 5 minus 12x squared. What did we do here? We had a difference rule. I'm just writing all of the ones that we used. We had a constant multiple. That was leaving the 5 out front and the 4 out front and differentiating the x term. And we used the power rule to do that. Again, the only one you really probably thought about was the power rule, and everything else just kind of happened. B. Y, sorry, this one's written in f function notation. F of x equals negative 3x to the power of 5 plus 8 radical x minus 9.3. This one has a constant, okay? The constant, just the derivative of any constant is 0. You can think about that this way. If you were to graph this line, y equals negative 9.3, it would just be a straight line with a slope of 0. Okay, so the derivative of that is 0. We're going to rewrite this first so that we can look at each term and differentiate it. I see that I have a root here, so I'm going to make that 8 times x to the power of 1/2. The rest will stay the same, and I'll drop the constant. And actually, if I'm calling it f of x, I need to leave that constant there until I start differentiating. The derivative of f of x is denoted f prime of x. And here are our rules. We have a constant multiple. We have addition and difference rules. So we're just going to take the derivative of each term individually and be mindful of the signs that we have. And we're basically just using the power rule each time. So here we have negative 3. The derivative of x to the power of 5 is 5x to the power of 4. Next term, we have a positive 8. The derivative of x to the power of 1/2 is 1/2 times x to the power of negative 1/2. Okay, the exponent goes down by 1 from 1/2 to negative 1/2. Close that off, and the constant, the derivative of that is 0. From here we can simplify. We've got negative 15 times x to the power of 4 plus 4 times x to the power of negative 1/2. And we're going to express as a positive exponent every time. So our first term is good. It's going to stay the same, negative 15x to the power of 4. But then our next term, 4 stays in the numerator, and the denominator becomes x to the power of 1/2. And I'm going to right away flip that into the square root. Okay? Are we comfortable with that? Again, each term on its own. C. G of x is equal to 2x minus 3 in brackets and times x plus 1. All right, to differentiate this, we first need to expand. Okay, you can't, there is no rule for doing the factors like this. You need to expand g of x first, okay? So we're just going to FOIL this. 2x times x is 2x squared. And then I have 2x times 1, which is 2x. And I also am going to have negative 3x's. So I've got positive 2x's and negative 3x's. That's negative x. My constant is negative 3 times 1 is negative 3. Now I can take the derivative of g of x, that's g prime of x. Looking at each term, here I have a constant multiple out front, that's 2. The derivative of x squared is 2x, so that's going to be 4x. And the derivative of x is 1, okay? It's essentially the exact same rule. You would take the exponent, there's an invisible exponent of 1 here. You'd put that in front as a multiplier, and then the exponent would drop to 0. Anything to the power of 0 is 1, so this just becomes negative 1. And the derivative of negative 3 is 0, so that drops off completely, and this one is done. I'm just going to fit d off here to the right. You can keep going down or put it to the right, your choice. It's a little bit longer, 1 or 2 extra steps in there. D is h of x, and this time we have a quotient law. In the numerator we have negative 8x to the power of 6 plus 8x squared over 4 times x to the power of 5. Okay, according to the quotient law, I don't even know if there is a quotient law, but you can split this into 2 terms, which is what we have to do. Okay, so this group at the top divided by anything means you have to divide this term by that and this term by that. So we can rewrite this. In the numerator, negative 8x to the power of 6 over 4x to the power of 5 plus 8x squared over 4x to the power of 5. Okay, now we can simplify this before trying to find the derivative.
Can we factor 4x to the 5 out of the 2 terms on top?
Yes, so we're going to factor out as much as we can. We're going to simplify this as much as we can before finding the derivative. So the constant here in this first term, negative 8 over 4, becomes negative 2. And there are 5 factors of x in the denominator, 6 factors of x in the numerator, so I'm just left with 1 factor of x in the numerator. And then in the second term, I have 2, and then I'm going to have 3 factors of x remaining in the denominator. So I've got 2 over x to the power of 3. Now again, we don't want our variable with its exponent in the denominator, so I'm going to express that as with a negative exponent in the numerator. So our first term is good, negative 2x. Second term is going to be 2 times x to the power of negative 3. So this is h of x simplified, and now you can see it's pretty straightforward for us to take h prime of x. Negative 2x, well, again, x to the power of 1, the derivative of that is 1. So this, whenever you have just x to the power of 1 and it has a multiplier out front, only that value remains. Okay, so the derivative of negative 2x is negative 2. Here I am going to do it in 2 steps. So I'm going to leave my plus sign here, and then I'm going to also have a 2, which is just going to stay there, and then I'm going to differentiate this x to the power of negative 3, which becomes negative 3 x to the power of negative 4. Simplify that. We get 2 times negative 3, which is negative 6 x to the power of negative 4, and express as a positive exponent means we're going to have negative 2 minus, in the numerator, 6 over x to the power of 4, h prime of x. Okay, that was pretty good. 4 quick examples with a whole bunch of different rules being applied. Again, not that difficult. Go step by step, go term by term. And if it's not in nice terms, then you need to work with the function, the original function first, just like we did in C and D, to simplify and then differentiate. Example 6 says, apply a strategy to determine tangent points for a given slope. So this time we're not going to find the slope at a point. We're given the slope, and we have a function that, a function could look like anything, right? So it could have the same slope at many points, right? The slope there, the slope there, the slope there. That's it. But those three are the same-ish, right? So we can see how that can happen in a function. So the function we're given is y equals x squared times x plus 3. So we're dealing with a cubic. If I wanted to kind of sketch out what this might look like, I can see that the most it is going to repeat itself, a slope is going to repeat itself maybe twice. Okay, so if it's on this side, it could be like that, or 0 and 0. But that's pretty much it. Positive slopes and zero slopes will repeat themselves. Negative slopes will not. So whatever they give us as a slope, the max it can happen is twice. And it's told that the tangent that we're working with has a slope of 24. I'm going to call that the tangent slope so that you have enough information to look at your notes again. So again, it's positive. It's cubic, positive cubic, and I just drew it out. We're looking for two separate spots here. First step is going to be expand and differentiate. Expand and differentiate. Okay, so y is x squared times x is x cubed. X squared times 3 is 3x squared. Now I can differentiate, take y prime, or dy by dx. It's going to leave me with the derivative of 3x squared plus 6x. And now, since this is the equation for the slope of the tangent at any point, and I already know the slope of the tangent that I want, all I have to do is say dy dx equals 24. Okay, so I'm just going to sub in dy by dx equals 24, because they told me that my slope would. And now we're probably already starting to see how we're going to get two solutions here. The derivative is a quadratic. So we've got 24 equals 3x squared plus 6x. And now I'm just applying all of my older math skills. I can't solve this. I need to have it set equal to 0 in standard form. So I'm going to subtract 24 from each side. 3x squared plus 6x minus 24. And now I'm factoring to solve. I notice a common factor of 3 in each of these terms. So I'm going to divide each term by 3. Conveniently, when I divide 0 by 3, it's still 0, leaving me with x squared plus 2x minus 8. And now this I can factor using sum and product. I'm looking for two numbers that will add to positive 2 and multiply to negative 8. That's going to be x plus 4, x minus 2. So this equation is true, that 3x squared plus 6x equals 24. That is true when, x equals negative 4 and x equals positive 2. Okay, what did that tell us? That tells us that when x is this value or this value, the slope is 24. Okay? But that's not exactly what we're looking for. We're looking for the points on the graph where this is true. So these are the x values. So to find the corresponding y values, find corresponding y values, I need to sub back into the original function to do that. Okay, so don't get mixed up. Don't sub it back into your differentiated your derivative. Also, if you did that, you'd just get 0, which you'd hopefully at that point realize that you made a mistake. But you got to sub these back into the original to find the point where the tangent has a slope of 24. So here we go. For x equals -4, scrolling up, we're going to go y equals -4 in brackets squared times -4 plus 3 in brackets. -4 squared is 16. 16 times -1 is -16. Therefore, one of the points is -4, -16. And over here we'll do for x equals 2. Again, sub it into the original. So that's y equals x squared. So I got 2 squared. I'm going to bracket it even though you don't need to. And in the next bracket, 2 plus 3. 2 squared is 4. 2 plus 3 is 5. 4 times 5 is 20. Which gives us the next point, 2, 20. Okay, these are the 2 points along this cubic that have a slope of the tangent of 24.
Wait,
So
are
something.
we supposed to look for the y values in the original function, not the derivative?
Yep, we did. We went right back up to the original.
Okay, I thought that was the derivative.
And we got x squared times 2 plus 3. Yeah?
Okay.
Yep, so you could definitely make a special note of that. Sub back into the original function. Example 5 is a word problem. We have a skydiver, and so this is going to be dealing with the speed of a skydiver, and we've got variables such as height and time, and if we take the derivative, we'd calculate speed at any point on the drop. So we have a skydiver. I'm just going to write some of the main information here. Skydiver jumps out of a plane jumps from 2,200 meters. His height above the ground in meters after the fall, after t seconds, is represented by h of t equals 2,200 minus 4.9 t squared. So 4.9 t squared is acceleration due to gravity. What does this assume? This assumes that there's no air resistance, nothing slowing him down, which is obviously impossible. But imagine you were in a big vacuum, not like a Hoover vacuum, but a vacuum as in a place where there's no air, no matter at all, which is also impossible. And then this would be the function that models his fall. So we're finding out how fast is he going, speed after 4 seconds. Right, underline the question. What's the speed after 4 seconds? Okay, the instantaneous rate of change of the height of the skydiver at any point is found by taking the derivative of the function that models his height. So we take h prime of t. 2,200 is a constant, the derivative of which is 0. And then here we have negative 9.8 times t. To find the speed at the exact point of 4 seconds, all we have to do is sub in to this equation the value of 4 for t. At 4 seconds, speed is 9.8 times 4, which our calculator will quickly tell you is negative 39.2. Okay, so he's falling to the ground. That's negative. He's coming down. And at 4 seconds, he's falling at a rate of 39.2 meters per second. meters per second. Height is measured in meters, time is measured in seconds, and that was not so challenging. Example 4. Applying derivative rules to determine the equation of a tangent. So again, finding the derivative allows us to find the slope of the tangent at any point along the curve. So we're going to be given a function, which is f of x equals 4x to the power of 3 plus 3x squared minus 5. And we want to find the equation of the tangent at x equals -1. Okay, so a couple of steps here. Number 1, we're going to use the derivative to find the slope at that point. Then we're also going to need the tangent point. Okay, so I'm going to do it a little bit of a different order than your book does, but I'm going to first use this function to find the tangent point, then differentiate it, and then use the derivative to find the slope. Okay, so I am going to right away find, so for the tangent point, what do I need to do? I just need to sub -1 into my original function. So I've got, wherever I see an x, I'm plugging in -1. 4 times -1 to the power of 3. 3 times -1 squared minus 5. -1 cubed is -1, so that's going to be -4. This is +1 times 3, that's plus 3 minus 5. We are looking at -6. Therefore, the tangent point is -1, -6. Okay, now I'm going to find the derivative of f of x. It's up there. I'm not going to rewrite it. I'm just going to find the derivative right away. So f prime of x, and actually see if you can do it on your own, and then double check your work here. Okay, at this point I'd be pretty comfortable skipping some steps, so I would just right away go 3 times 4 is 12, x squared. So I got 12x squared, and plus 6x, and the constant drops off. Okay, so finding the derivative is not all that challenging. Now we need the slope at -1, -6, specifically. So we're putting into our derivative, f prime of x, we're going to put an x of -1, which gives us 12 times -1 squared plus 6 times -1. -1 squared is +1, that's 12 minus 6, which is 6. So that's the slope at the point. Now we have a point, and we have the slope. Find equation of tangent at x equals -1. All right, so we have our function of the tangent line, okay, is, the slope we found is 6, and the point is -1, -6, and we just need the equation of a line. Well, we're going to use point slope form. That's y minus y1 equals slope times x minus x1. So we have y minus -6 equals our slope, which is 6, +6, times x minus -1. And now we're just working on simplifying that. Okay, so our point, x, y, came from our tangent point, and the slope is the slope of the tangent at this point, which we found using our derivative and subbing in our x value. So this is y plus 6 equals 6 times x plus 1. And now we can simplify. We've got y equals 6x plus 6 minus 6. So what did I do there? I distributed the 6 to x and to positive 1, and I also subtracted 6 from both sides. And that leaves us with y equals 6x, and that's it. Y equals 6x. That is the equation of the tangent line on the curve 4x cubed plus 3x squared minus 5, all right, at the point x equals -1, or -1, -6. And again, you could do this on Desmos using that slider that I posted on Edsby. Just change the function to the function that we were given. And scroll down to x equals -1. Practice problems to be responsible for come from page 83. And you should be able to do 1 through 15. Again, you don't need to do all of them. Do what you need to do in order to practice the skills that we learned.